Imagine a tuning fork striking air, sending ripples that travel through the room. Those ripples are sound waves, tiny pressure pulses moving like a marching army of molecules. In this lesson we uncover how these pulses form, move, and shape everything we hear. Sound begins when a source pushes air molecules apart. These pushed molecules collide with neighbors, creating a compression zone. The compression travels outward as a pressure increase moving through the medium. After the peak, molecules relax, forming a refraction where density drops. Refraction follows compression, completing one full oscillation cycle of the wave. The pattern repeats as long as the source continues to vibrate. Each particle moves only slightly back and forth along the direction of travel. Because particles shift longitudinally, the wave is classified as a longitudinal pressure wave. The speed of this wave depends on the medium's density and elasticity. Thus, sound propagates through air by successive compressions and refractions carried by molecules. Pause 0.8. A tuning fork vibrates at a fixed frequency, oscillating its prongs back and forth. As the prongs move outward, they push on adjacent air molecules, creating a region of higher pressure. When the prongs retract, the compressed molecules expand, leaving a zone of lower pressure behind them. This alternating pattern of compression and refraction travels away from the fork as a longitudinal wave. The distance between successive compressions is called the wavelength, while the time for one vibration cycle is the period. Because air molecules are closely packed, they quickly transmit the disturbance to their neighbors, sustaining the wave. The speed at which this pattern propagates depends on the medium's density and elasticity. In air it averages about 343 meters per second. As the wave moves outward, its energy spreads over a larger area, causing the amplitude euros and perceived loudness euros to decrease with distance. If two waves meet, they interfere. Constructive interference amplifies pressure peaks, while destructive interference can cancel them out. Understanding this mechanism explains why we hear sound and how instruments produce different tones. Pause 0.8. Sound travels as longitudinal waves that push and pull particles in a medium. In solids, the tightly bound atoms create high elasticity, allowing rapid transmission. The speed of sound in a solid is roughly proportional to the square root of its elastic modulus divided by density. Water, a liquid, has lower elasticity but higher density than air, giving it an intermediate speed. Air molecules are loosely connected. Their low density and modest elasticity produce the slowest propagation. Attenuation occurs when wave energy is absorbed or scattered, reducing amplitude over distance. Solids absorb less energy because collisions between atoms are efficient at transferring momentum. Liquids dissipate more due to internal friction as layers slide past one another. Gases lose energy quickly through viscous drag and thermal conduction among sparse molecules. The combined effect of elasticity and density explains why a drum beat sounds louder in wood than in water or air. Visualizing wavefronts side by side helps students see the clear differences in speed and damping. Pause 0.8. Sound travels as a pressure wave that oscillates back and forth. The speed of sound in air is roughly 343 meters per second at room temperature. Frequency counts how many oscillations occur each second, measured in hertz. A higher frequency means more cycles per second and a higher perceived pitch. Wavelength is the distance between successive peaks of the wave. Because speed equals frequency times wavelength, a fixed speed forces an inverse link. When frequency rises, wavelength shortens. When frequency falls, wavelength lengthens. The human ear can hear frequencies from about 20 to 20,000 Hz. On our graph, the audible range is highlighted with a shaded band. Each point on the curve shows that as frequency increases, wavelength decreases linearly. This relationship explains why high notes sound sharp and low notes deep. Understanding this helps in designing instruments and acoustic spaces. Pause 0.8. Sound waves are mechanical vibrations that travel through a medium as alternating compressions and refractions. The peak value of the pressure variation is called the amplitude. It determines how much the air molecules move. When the amplitude increases, the sound pressure level rises, which our ears interpret as louder noise. Decibels provide a logarithmic scale that maps these pressure amplitudes to human perception of loudness. A small increase in amplitude can produce a noticeable jump in perceived volume because of the ear's sensitivity curve. Energy transport is directly linked to amplitude. Higher pressure peaks carry more kinetic energy per unit area. The intensity, measured in watts per square meter, equals the product of the squared amplitude and the wave speed divided by the medium's density. Thus, louder sounds not only feel stronger, but also deliver greater mechanical work to their surroundings. In everyday life, a vacuum cleaner at 70 dB has roughly 10 times the intensity of a whisper at 30 dB. Visualizing these relationships helps students connect abstract equations with tangible acoustic experiences. Pause 0.8. A single pulse travels along the taut string toward the left euro's hand boundary. At the fixed end, the wave inverts and returns to the right. The returning pulse meets the incoming one, creating a superposition of amplitudes. Where the peaks align, constructive interference amplifies the motion. Where troughs meet, destructive interference cancels it. Over time, nodes at euros points of zero displacement to euros appear at fixed positions along the string. Between nodes, antinodes form where the amplitude reaches its maximum during oscillation. The resulting pattern of nodes and antinodes is a standing wave that persists while energy feeds it. If the boundary were open instead, the pulse would reflect without inversion, altering the interference pattern. In acoustic terms, a rigid wall produces a pressure node at the surface, while an open end creates a pressure antinode. When two sound waves meet in air, their pressures add. Constructive peaks reinforce loudness. Conversely, opposing troughs cancel, producing a quiet zone that can be heard as an echo when reflected back. Pause 0.8. Sound is a longitudinal pressure wave produced by oscillating particles. A vibrating source displaces nearby molecules, creating successive compressions that propagate through any medium. The speed of propagation depends on the medium's elasticity and density, while frequency determines pitch and wavelength, and amplitude governs loudness and energy transport.